This is Mrs. O'Neill for AP Chemistry, Chapter 14, Section 2, Reaction Rates. You should have watched the intro lesson on the rate of reaction. Here are my notes. So we need to understand that every reaction has a certain speed to it. Some are really slow, and some are really fast. So it just depends on the reaction. So they're going to be different for the different reactants and products. Obviously, the quicker the reactants turn into products, the faster the reaction rate. So it gave you a nice little flow chart as always. So reaction rate over time. So again, over time, what happens to the concentration of those reactants? And over time, what happens to those concentrations of those products? So here he has a nice little formula that we will put in our notes in a moment. But notice that there's a negative in front of the reactants and a positive in front of the products, because the reactants are going to disappear. That's why they get that negative. That's all that negative is there for, is just to signify that it is decreasing the reactants, the amount of reactants. So we just have that negative in there, and the positive for the products because they are appearing. So that's all that positive and negative is truly for. So of course we can measure it. He did that FETS simulation, and what are some of those factors, and we will get into those a little bit more detail throughout the chapter, but we're going to talk about how increasing temperature increases the rate of reaction and so on, like concentration, pressure, and surface area. So on to your packet of notes. The objective for this section is determine how to express reaction rate according to how the reactants are disappearing and how the products are appearing, and how they are actually related again to that stoichiometric reaction, right? Those coefficients in that balanced reaction. So again, pause the video and then write the words and then play the video to hear my words. So rate is just determined by the disappearance of a reactant, or it could also be measured by determining how much product is appearing. So rate is just a ratio between how much reactant is disappearing over time or how much a product is appearing over time. So if we think about just our normal rate, like we're driving a car or racing in a track field, right? It's miles per hour, right? So it's always going to be a ratio of distance over hour. Well, in our case though, in reactions, we're dealing with concentration per, usually it's seconds. Most reactions do happen in a matter of seconds and not in a matter of hours. However, some reactions do take as long as centuries to happen. So again, the reaction rate is just how the speed is. So the speed is that ratio between the concentration and the time, right? So if we want to know how much the reaction is going or how fast the reaction is going, we would do a change in concentration of our one either reactant or product over the change in that time. So again, it's just our difference in concentration over difference in time. So reactants versus products. So disappearing reactant will be negative. I said that before, right? Because the reactant is just disappearing. That's the only reason for that negative there. And the products are appearing. So that's the only reason for that positive notation. So if we look at rates here of a chemical reactions are often measured as a change in the number of moles. So it's either going to be moles or concentration over a given time. So here we have our red squares signifying those are the reactants. Notice our reaction down here. Okay. And as we go on, look how the reds are disappearing. And now we have our blue circles appearing. So I'm just going to quickly go back there. So we have our reactants only. And as the reaction goes on, so we have a couple of minutes there, and now we've made some product. Notice we have some more time, more product, less reactant. Again, less reactant, more product, and so on. So if we look at all of them, again, as time passes, the amount of reactant, those red squares, decrease. Obviously, then the amount of product has to increase. Again, because a balanced equation tells us no matter how much we start with, we have to end up with, right? That law of conservation of mass. Those atoms are just going to be rearranged in a different way. So assuming equal time intervals between those boxes, how can you tell that the rate of conversion of reactant to product is not constant throughout this reaction? Well, because of that collision theory, atoms, ions, and molecules react to form products when they collide with each other. They need to provide that colliding particles have enough energy in order to make those products. And we're going to learn that it's not only that they have to collide with each other, they have to have enough energy to collide hard enough with each other and at the correct orientation. Otherwise, those products do not get made. So it should make sense at this point that the less reactants you have, the less amount of product are going to be made over time. So if we look at what's called the Haber process, we have some nitrogen, hydrogen mixing with each other to make ammonia. We're going to look at this in a different way now using the balanced chemical equation. So we want to remember we have 1 molar of nitrogen to 3 molars or 3 moles of hydrogen to form those 2 moles of ammonia. So if we look at our hydrogen, this is going to be our curve for hydrogen, right? Our concentration over time is going to decrease. That should make sense because that's a reactant. So as the reaction proceeds, the amount of hydrogen is going to decrease. Now, what's happening to the nitrogen? Well, the nitrogen is going to go down 1/3 as fast, again, because of the 1:3 ratio between the nitrogen and hydrogen. So it's going to decrease 1/3 as much, or 1/3 as fast, versus the ammonia. Now remember, the ammonia is the product, so it starts at 0. It has no concentration in the beginning, and of course it's going to increase over time. And how is it going to increase? Well, it's going to increase 2/3 of that of the hydrogen, right? If we're comparing it to hydrogen, if that's our starting point. So we want to remember that concentration changes, but the rate is equal, and that's going to be important later, right? The rate at which this happens is going to be equal all the way through. It's the amount of the nitrogen, the hydrogen, and the ammonia. The concentration is changing. So change of rate with time, again, as the reaction proceeds, the rate decreases because the concentration of those reactants is going to decrease, okay? So again, looking at that graph, we can see that, again, we are decreasing according to the molar ratio, and we're increasing products according to the mole ratio, okay? So that rate is kind of going at an equal speed according to how much reactants or how much products are being made, okay? So the average rates are over a long interval. So we like to say that the rate is an average, okay? So an average slope method would be this. Okay, and we're not going to go crazy, but we're going to hopefully get you to understand where the numbers are coming from. So that's why we have a change in concentration of H over a change in time. But notice it's a curve. It is not a straight line, so it's not constant, okay? But there is a thing called instantaneous rate, and that's determined by finding the slope of the tangent line, which you will never have to do. They will give that information to you, or they will give you a graph, or they will give you exactly where they want you to have those 2 given points to find the exact rate at an exact moment of that reaction. So instantaneous slope would be a tangent to this line, right? Because it's a curve, we would need that tangent in order to find the actual instantaneous rate or instantaneous slope right at that moment. So read this over. Hopefully this makes sense now between instantaneous rate, and we will not be doing this, and we will not be doing calculus. So now give this some thought. What is the difference then between average and instantaneous rates? Hopefully that makes sense. And in a given reaction, can these two rates ever be the exact same numeric value? Of course they can, right? Especially if we have some kind of plot that makes that concentration versus time linear. So if we look at reaction rates in that stoichiometry, notice again, we have little a is our coefficient. So it's 1 over our coefficient, change in that substance over the change in time. Now notice there are 4 things here that equal each other because the rate of this disappearing equals the rate of this disappearing equals the rate of this appearing equals the rate of this appearing. And we want to make sure that we understand those negatives are there. Why? Because they are disappearing. That's really the only reason for that negative. And you're going to see with the numbers, it will make sense. So again, if we notice our Haber process that I showed you before, if we were to write it out, what would be that rate equation? That's what it would look like. So another example is this. So look at that example. Make sure you're understanding why negative versus positive, why the 2 and the 4 versus nothing is here, and understanding what we can say that explains the rate of these disappearing reactants versus the rate of the appearance of products. And here's one more, very similar. So here's an example. See if you can kind of read the example using the formula now that you just got and understand using the stoichiometric reaction. See if you can figure out A and B. And of course, B, I'm going to give you some kind of graph. So A is like this, right? So our solution is calculate the average rate of just this guy, the C4H9Cl over time. So here's our equation because everything is a 1-to-1. Okay, it is negative, and notice it has to be negative because of our numbers, right? If it's disappearing, you really can't have a negative rate, right? Rate has to be in the positive sense. Rate is always something per time, right? It's always in the positive sense. So you do need that negative in order to make sure that our ratio turns into a positive number. And this, in this case, it's molarity per second. And I did this second -1 because you're going to see that a lot when we get to the next section when we deal with our K constant. So negative again is to make rate positive. So again, here's our B. If you want to quickly sketch the graph, I would have to give you this, or AP would have to give this to you. So there's our tangent line. And again, we're going to do change in Y versus change in X. Again, I'd have to give you those numbers. Those numbers are given to you here, so use those specific numbers. And again, it's negative because we are dealing with a reactant, but that's going to change it then to a positive. That negative in front is telling us that those are reactants disappearing, as well as we have to have that rate into a positive sense. Okay, give that information to you. So again, how about if we don't have that 1-to-1 ratio? Here's some examples of how it's a 2-to-1 ratio in this case. But again, look at your equation, right? -1/2 because of the 2 is going to equal positive 1/1, so you don't even have to write it, equals that positive of the appearing of iodine. So again, if we have something like this, if I'm giving you the rate of 1, can you formulate an equation and then solve for what it's asking you of? In this case, here's our equation. So if you got the equation, I'm happy. Again, notice the negative. Now, can you plug and chug the information they gave you, rearrange the equation, and get an answer? Something like that. Again, plug and chug. So it's going to be 2/3 this value that they give you, right? This is what we're solving for. So it's giving the 2/3 of that value. And again, there's our answer. And it's molarity per second. Remember, it's concentration over time. And rate always has to be in the positive sense, right? Rate is always how fast something's going. You're never going to have a negative rate value. See you in class.